In this demonstration, we will set up a small drainage model in SWMM, run the model, and look at the hydraulic modeling results. First, we will start the SWMM desktop application. The model I am going to create consists of 1 hectare area of catchment connected by a drainage pipe to a storage tank, and then the outlet of the storage is diverted to an outfall. So let's start with the catchment. Remember, in SWMM the shape and size of this catchment representation is not really important unless you are using this feature called auto length, which can be used to calculate areas and dimensions, but we are not going to use that. So here's our catchment, and then for a drainage simulation we need at least one metallurgical object related to this catchment, that is a rainfall or rain gauge object. So let me create one of those, and then this is the upstream node to which this catchment is flowing into. Then I have a storage, and finally the outfall. Now I will connect these with conduits. Okay. The basic model skeleton is ready now, and we have to go on inputting data for each of these components. Let's first start with the rain gauge object. Suppose that we are trying to simulate a simple design rainfall. In SWMM there are several ways to represent rainfall, and I will use the default mechanism called time series. This requires me to give a name of the time series that I am going to use in this rain gauge. Let me call it rain 1, and at the same time I will give it a name for the rain gauge, RG1. And this reminds me of one more thing, that is, at the moment we are using this imperial unit system. So I will change it into the international cubic meter per second system. Let's go back to the rain gauge. So we need a series called rain 1. So let me create that time series here. In this data flap there is an entry called time series. At the moment we don't have any time series in this simulation system, so we will add one, and here it's important to name this as rain 1 because that is the name we gave in the rain gauge object to our time series. And let me add a couple of values of rainfall to represent our design rainstorm. And this design rainstorm is measured at 5 minutes interval. Finally, this is the design rainstorm that we have defined. It lasts for a period of 25 minutes, starting with the value 2 millimeters within the first 5 minutes, 5, 10, 5 and 2. Now let me go back to the rain gauge just to check whether everything is okay. Series name is rain 1. And the rain unit should be in millimeters. Now I will go to the catchment object. I will give this the identification tag C1, the name C1, and the area of this catchment is 1 hectare. Let's assume that this is a square catchment, then one side will be 100 meters. And slope is 0.5%, let's say, and 50% of this catchment is impervious. Let's say the impervious fraction is made of concrete, so this is a good value for concrete, and the pervious fraction is made of grass. Now by pressing F1 at any stage in the model setup or simulation within SWMM desktop, you can get access to the help system, and help is context sensitive. For example, I press F1 here just to see the typical values of Manning's N, and here is a list. So for the short grass it's 0.15. So that is the value I am going to use for this simulation. I am not going to change the destination storage values for this simple simulation, but I am going to change the infiltration calculation method into green amped. But you can see that you cannot change that here in the infiltration editor, because in EPA SWMM one model can have only one infiltration calculation scheme. You cannot have different infiltration calculation schemes in many catchments in the same model. So because of that, logically the selection of infiltration method is done at the project level. So let me close this. So in order to change the infiltration computation method, we will revisit this data tab here, and then select options and general. Here you can select the model wide choices like infiltration model to be green amped, and at the same time let me select the routing model to be dynamic wave, and also the time steps that we use for the calculation. I want to report my results at every 1 minute period. And my routing step will be a rather small value of 5 seconds. When you are using the dynamic wave method, you have to be really careful to select a small enough value for the routing step so that model does not lead into any instabilities. Let's go back into our catchment object. Now infiltration is changed into green lamped, and give the values for the infiltration model parameters based on the kind of the soil you are trying to model. Let's assume that we are going to model some sandy soil. Let's say a kind of sandy loam. So let's select values from these typical parameters given here. You have to remember that the help files in SWMM gives its parameters in the imperial units, so you have to do unit conversion to get these values into, for example, hydraulic conductivity into millimeters per hour instead of inches per hour, and suction head from inches to millimeters. So I will input the typical values for sandy loam, about 60 millimeters of suction head, hydraulic conductivity of about 30 millimeters per hour, and initial moisture deficit as a fraction about 0.4. At this stage we have to indicate where this subcatchment is pouring water into. It should be this junction, junction 2. I'll give a better name for this. Let's say J upstream. At the same time I will give names for this: ST storage, OF outfall, and conduit 1 and conduit 2. Now I want to connect C1 to JU. To do that, I will indicate the outlet of C1 as JU, simple. So the connection is indicated by this dotted line here. This is drawn automatically once you indicate the correct pour point for the catchment. I will also indicate the rain gauge that is associated with this catchment, that is RG1. Okay. At this stage, actually, though it does not mean much, we will be able to run a simulation. Here we get some error, that is error 159. The recording interval is greater than a time series interval for rain gauge RG1. So that is a mistake I made when I was specifying the rain gauge. So let's go back to the rain gauge object and see where I have made this mistake. So here is the time series that we use to define the rainfall for this. But if you look at this time interval parameter here, it indicates 1 hour, whereas our rainfall is measured at 5 minutes. So it is this value that caused that error. So we will change it into something like 5 minutes and try again to run. And this time the run was successful. Whenever you run a simulation in SWM, the interface will show you some very important two parameters: the continuity errors, that is the mass balance errors for the surface runoff, that is the runoffs in the catchments, and in the flow routing, that is in the network. Always make absolutely sure that these two values are not overly large. These are very much indicative of any problem, like instabilities that you may have in the model. Even though we were able to run the model at this stage, as I told you before, the results won't mean anything because we did not complete setting up all the parameters the way we want them to be. So let's go back one element by one and start specifying the parameters for those elements. The first junction, and the maximum depth, let's specify as 1.5 meters here. The outfall, let's set the elevation to be 0, okay, and the elevation, the invert elevation at the storage, set to be 1. Then the properties of the conduits, let's assume circular pipes with diameter of 100 centimeters. Length 100 meters each, and assume that these are made of concrete, the typical roughness for concrete. The properties of the storage. EPSWM has many different ways of specifying storage. Here we use the so-called functional storage curve, and we assume a constant cross-section of 10 meters squared and the maximum depth of 1 meter. So we have here we have a sort of tank of cross-sectional area of 10 meters squared and 1 meter high. At this stage, it is possible for us to meaningfully perform a simulation because all of the parameters that we are interested are also already specified. So let's run the model and check the continuity errors. They are quite small indeed, so no problem there. And now let's look at the results. First, I will check the status report, which gives you a text-based summary of the simulation. You can check the continuity errors also in a detailed fashion here. What I am interested in primarily here is about flooding, whether there is any flooding, that is where the overrunning of capacity of the system somewhere. Here we see that we encounter flooding in the first upstream junction, JU. So I have to do something in order to prevent this flooding if this is a design exercise. I will attempt to do that by upgrading the sizes of these conduits. Instead of 100 centimeter, I will go for 200 centimeter pipes. And let's check the situation now. Now we can see there is no flooding. At this stage, we can have a look at the more detailed aspects of the simulation results. For example, we can see what happens in the cross section from junction JU to the outfall OF. To do that, I will click on this profile tool and I will specify JU as my starting junction and OF as my end junction, and then click this button called find path. It will automatically find the path between JU and OF as indicated here, and then we can see a profile plot. Next to this data tab, there is a tab called map, where you can play an animation of this profile. I will do that. And here we can see an animation of the flow regime. You can clearly see that none of these pipes are surcharged, and this is the height of our storage, and storage is not overflowing. But if we play this back again, one more thing you will notice here is that we are not at all utilizing the 1 meter height that is available in the storage effectively. Storage is filling up only marginally, so we have to do something about this. In order to utilize the full volume of the storage, I will do a small modification into this network. I will do that by introducing a small orifice into the outflow of the storage. So let me add another junction here, and I will name that as ORJ to indicate orifice junction. And now I want to connect this conduit C2 not to the storage directly, but to ORJ. So here I will change the inlet node of conduit C2 from ST to ORJ. Sorry, should be ORJ, right? And then I will go and add an orifice from the storage to ORJ. So this is the orifice, and I will set a small opening in the orifice. It's a circular cross section, and let me make the opening somewhat small, like 50 millimeters. Also, I have to make the invert elevation of the orifice node at the same elevation as the storage unit. And here is the cross section, and now let's look at the animation of the flow regime. And now we can see that the upstream pipe is of course surcharged, and we are utilizing the storage very effectively, and the pipe downstream of the storage has very low flow as expected because of the regulation action of the storage. At this stage I will have a look at the status report again, and especially about the stability situation, whether there are any instabilities. The link 1 has highest flow instability situation, and the routing time step, what we specify seems to be right, because if it is not small enough to be stable, usually SWMM internally adjusts the time step. Now let me show you some other tools that you can utilize to look at the simulation results. You can make graphs, for example. You can plot the links, the flow, and the flow in the link, and let's select some links here, C1, the orifice, and C2. And here you can clearly see how the orifice and the storage system is regulating the flow downstream. This is the upstream hydrograph, this one, and this is the downstream hydrograph. How about the storage? Let's look at the depth. And storage is very nicely utilized because we have 1 meter height and about 0.9 meter is utilized in this situation. I hope you gain some insights into the capabilities of the SWMM 5 desktop application. Of course, I did not show all the features of this application during this demonstration, but I hope this would be a good starting point for you to start exploring this software much more in detail. Good luck.